What we're doing today is not all that different from yesterday. We're adding on an extra step. Otherwise, we've done the bulk of the work. So these questions will be similar to the ones we did yesterday. And you're probably, well, very soon we're going to get into using derivatives to do things. We already have a little bit when we found equations of tangents and stuff, but really that's just extra practice of other stuff. In the next unit, we're going to start actually using derivatives to solve problems, that kind of thing. So this is sort of a peek into that world. Okay, so we'll start with this first one. It's pretty simple, pretty straightforward. Go ahead and take the derivative. Are we done? No, I hope not. It says we're supposed to fully simplify. We're going to see a little bit more why that's important. We talked about a bit about it yesterday, I think, but about why we really want to fully simplify and how helpful it is. So I think I can common factor a 6. Oops. 2x squared. And then I've already checked, and b squared minus 4ac is 25. You can double check that if you want, but I'm pretty sure it's true. So this is factorable. And it works out to that. Everybody happy with that? So that's no different from yesterday, and that was a lot simpler than the ones we were doing yesterday. There's not really a lot of other simplifying to do there. Like there's none of the big simplifying we were looking at yesterday. It was just a matter of factoring it. Now, here, so then we're supposed to do these two extra things. The values of x where the derivative is 0 and the values of x where the derivative is undefined. And here's the tricky part where, you know, over the next I don't know, a couple of months at least or something probably. We're going to be doing this. We're going to be doing all this work getting derivatives, and you're going to be staring at multiple functions. Generally speaking, the function that we care about is the original one. That's the one we're working on. That's the one we're going to be doing something with. We're going to use the derivative to inform us about the original function. But right now, we're asking a question about the derivative. So when is the derivative equal to 0? Somebody answer that question? Yeah, very good. When x is -2 or 1 over 2. So just the solutions to setting the derivative equal to 0. Now that tells us something about the slope of the tangent at that point of the original function, right? But this one is just simply, when is this function, which is a quadratic, like we know a lot about quadratics, right? So we're asking a question about the derivative, when is it equal to 0, but it's going to tell us something about the original function. The original function was cubic, its derivative is quadratic. Okay. Now, when is f prime at x does not exist? Or another way of saying that, when is it undefined, or when does it does not exist? Anybody have any thoughts on that?
It always exists.
It always exists. So you would agree it does not exist nowhere? Kind of a strange way of saying that's double negative. So usually in this case, we would say something like this. Daniel, why do you say that?
Because it's a polynomial and it's never being divided by anything?
Yeah, it's a parabola. Like, again, we know a lot about these functions. It's polynomial. All polynomials have a domain where they exist everywhere. What kind of things cause a function not to exist? Very good. Anything else? Yes, good. Anything else? A whole. And then sometimes some functions just have a limited domain. They don't exist everywhere. But those are the kinds of things we saw in MHF that would cause a function not to exist. Very good. What does all of this mean? What do we know about this cubic function, the original function that's up here? What might it look like? All the way back to the beginning of MHF, it's got a positive leading coefficient. It's odd degree, it's degree 3. Would you agree it might probably sort of look something like that? Yeah? That's what cubics kind of look like. They can look like other things, but there's a good chance it looks something like that. So what does this information that we've done here tell me about that graph? What does it mean when the derivative is 0?
It tells you that one of the I'm going to say vertexes is at -2 and the other one is at 1/2.
We often call them turning points when they're not like the vertex of a parabola, but that's good. We all know exactly what you mean by that. So this one would be -2 and this one would be +1/2. Like, it's telling us the x values where these turning points occur. If I wanted to sketch this and I wanted to sketch it more accurately than I could in the past, I could take those x values, sub them back into the original equation to get the y values of those points, and I could plot those turning points more accurately, which is kind of where we're going to be going with all of this. Not so much with polynomials, but you could do it. Okay? So that's the whole point, is again, when the derivative is equal to 0, the slope of the tangent at that point of the original function is 0. That's some kind of a turning point. Not necessarily, but there's a good chance it's like a turning point. It's something interesting is happening there. There is sometimes more exploration we have to do to see exactly what it is, but for now we can just think of it like, okay, so it's a turning point or something like that. We also call them local max and min or local extrema. Okay, and it turns out that also where the derivative does not exist can also be where something interesting is happening. Sometimes it's not very interesting, but often, or sometimes I should say, not often actually. Often it's not interesting, but sometimes it is. And so when we take the derivative, we need to check both of these things. And you don't need to do this now, but eventually what you're going to be doing is interpreting. Is there something interesting happening there, or can I disregard it? Any questions about that? So for today, what we're practicing is stating when the derivative is equal to 0, when does it not exist? But just so you know, so you have some context of where this is going, because I think that helps us understand what we're doing and why we're doing what we're doing. That's why. Okay, it's going to tell us something about the original function. But when you take the derivative, then you think of the derivative as a function in and of itself, and you're asking questions about it. Does that make sense? So let's try this one. It's a bit trickier. Again, you can go ahead and get started. So I've mentioned this before, and I think most people are probably on the ball with this. You don't have to do it. You can do it however you want, but it does save you a line of writing. It can save you a whole line, so it can be useful. I'm going to take the derivative of the first part, which is 3x plus 1 all squared, which means I bring the 2 out front. Normally I would do that, times the brackets, and subtract 1 from the exponent. But then you're going to multiply by the derivative of what's inside, which is just 3. That's so simple that if you can start challenging yourself to be like, okay, so I'm bringing down the 2, and I'm going to multiply by what's the derivative of what's inside, so times 3, that's going to be 6. And most of you are probably already there. But if you're not, that's why that's a 6 and not a 2, okay? I've already multiplied by the derivative of what's inside. If the derivative of what's inside was more complex, like a binomial or something, then that's not helpful. So subtract 1 from the exponent and I get a 1. I've already multiplied by the derivative of what's inside, so now I just multiply by the other thing. Then I go plus, and I'm going to bring down the 3, and again I'm going to multiply by the derivative of what's inside, which is 5, so that's actually going to be 15. 5x minus 2 squared, and then I'm going to multiply by the other thing because I've already multiplied by the derivative of what's inside. And this is where now hopefully we are convinced and we understand why it's useful to take this further and simplify it. And this is one that requires the more complex factoring skills that we looked at yesterday. So what I notice is I've got a common factor that I can pull out of the 6 and the 15. I've got a common factor that I can pull out of the 3x plus 1 brackets that are common between both. And I've got a 5x minus 2 bracket that's common in both. So I can common factor all of those things, which is very normal. If you didn't get a chance to do the practice last night, I understand you have other courses and you were prepping for the quiz. When you go and do it today, this is something that's, I think, complex enough that you need to practice a few times. Yes, it's just common factoring, but it's different enough from the types that you've done before that is really worth looking at. And there are some patterns, some things that will become familiar that just always make your life easier. So I'm looking at this bracket right now, and it's 3x plus 1. I've got one of them here and 2 of them here, so I can only take 1 out. And 5x minus 2, I've got it cubed and squared, so I can take out the smallest exponent, which is squared. And this is the part, again, that's like, it's not hard, but it's just unfamiliar enough, I think. 6 divided by 3 is 2. 3x plus 1, I took that all out, but I had 3 of this, and I only took out 2, so I've got 1 of it left. 15 divided by 3 is 5. And again, I had 2 of these. I took them both out, but I had 2 of the 3x plus 1, and I only took 1 out, so I've got 1 of those left. Not done yet, because we can still finish up with this second bracket. So this is 10x minus 4 plus 15 plus 5. 15x. So I believe that's 25x plus 1. We good with that? And once we've done all like this, that was all the hard work. The rest of it is pretty easy. The next step, once you get into it, is pretty easy. You're just reading this information from your final form of the function that you've come up with here. So f prime at x equals 0 at x equals negative 1/3, 2/5, and negative 1/25. And again, this is just polynomial. It exists everywhere. The degree of it is 1, 2, 3, 4. We don't need to know that, but it happens to be. And the degree of the first one was 5, and that all makes sense. That all fits. But this is another way of saying f at x. F prime at x exists. Does anybody know what that symbol means? An upside down A. Ever seen that before? You know how, like, when we're doing domain and range, this means in, or is an element of, this means such that. This is another one of these formal logic symbols that we use. It means for all. So you might see it in the solutions, you might see it around. I'll often use it. That's usually how we would say it if it exists for all x. You can say does not exist nowhere if you want, but okay. Any questions about that one? All right. Now this one is a type that you will see a lot of throughout the course. Some of the ones we do in this unit to practice our algebra skills, to get used to the rules, to apply the rules to kind of bigger functions, but we won't really see functions like that throughout the rest of the course. This is one that we will. It looks familiar. It looks like something you would have sketched in MHF, don't you think? That could have been a question on a test in MHF. Okay, so y prime. The derivative of the top, which is 16, times the bottom, minus the derivative of the bottom, which is 2, times x minus 2, times the top. And you might have included, I'm going to do that in 2 steps because I think it's worth it for the lesson, but you could, again, that's a place where you could probably have simplified that. In this case, it won't actually save us any work. So it didn't matter. Whoops, that should be to the 4, all over the bottom squared. So the derivative of the top times the bottom. I should have mentioned this before. Some people are writing the product rule backwards. It's strange just to me when I go to market because I'm not expecting it, but it's not wrong. But if you do the quotient rule backwards, it's wrong. It's the derivative of the top times the bottom minus derivative of the bottom times the top. You cannot flip that. A minus B is not the same as B minus A, right? So be careful. Be very aware of that. I'm going to common factor the top. This second part is a product. It has a 16 in it. Like if I did it over here, it'd be 32, but I'm not going to bother because I'm just going to factor it out anyway. So I can factor out a 16 on top, and I can factor out an x minus 2. Then I'm left with 1 times x minus 2 minus 2, this 2 I haven't used yet. I've used that. I've used a 16, so I've got the x left. If that was too much, just simplify it first. Do it the way that you want to do it. Like you don't have to do it the steps in the same order that I'm doing it. But sometimes it's nice to see different ways of doing these things and different little tricks that you can look for or whatever. Yes?
Would there be a bracket around the x minus 2?
Doesn't have to in this case, does there? There kind of was, like it came from a place where it had brackets, but there's no reason why in these brackets I need it. Don't you agree? And oh, look what I can do here. This is 3 products on top, and one of them is common with the thing on the bottom, so that's important. X minus 2x is negative x minus 2 over x minus 2 cubed. I'm going to factor a negative out of this. Be careful. These brackets are not the same. Negative x minus 2 is not the same as x minus 2. And I think it's a little bit easier, some of the next steps, if I common factor that out. Okay. Now, this one's a bit more interesting. Where's this function? F, oh, no, it's not f prime. Where is y prime equals 0 when? Emery?
When x is negative 2.
When x is negative 2, why?
Because that's 0. That's max or min.
Yeah, that's because the function is 0 at negative 2. What's another way we can think about that? When the top is 0, right? So this is when the top of the fraction is 0. Anywhere else? I don't think so. Y prime does not exist when? Why? Huh? Yeah, when the bottom is 0. What else do we call that? It's a vertical asymptote. So remember, we're talking about the derivative here. That's what we were analyzing. We know that's telling us something interesting about the original function. We don't know exactly what yet, but there might be something curious there. So the function, the derivative function, has an asymptote when x equals 2 because the denominator was 0. And by the way, you could use technology to sketch this and think about it, and to sketch the original function and think about how they're related and that kind of thing. That might be a useful little thing as you're doing this, if you've got a computer up, I would be doing some of that, okay? So at x equals 2, the derivative does not exist. Can somebody tell me something about that? It's a whole, why do you say that? So this canceling here. When you have a hole in a function like that, but you still have a factor on the bottom, it's not going to be a hole, it's going to be a vertical asymptote. But you're right, that did happen up there. Somebody tell me something else about that. Bradley.
The function is also has the asymptote.
That's exactly right. So the derivative doesn't exist because the function doesn't exist. If the function doesn't exist, the derivative will not exist. Like it can't take the derivative of something that's not there. Okay, so this is, and you don't need to know this right now, but this is something that's interesting in that this is what we'll do later, is we'll say, okay, so the derivative does not exist, but turns out I don't really care because the function does not exist. Function, original function, so original function has a vertical asymptote. So does the derivative, but so did the original. That doesn't always happen, but in this case it did. Any questions? Yeah?
So what if like original function doesn't have like as an asymptote somewhere else and the derivative as an asymptote somewhere else?
So there's more testing that we do to check and see what's happening. Like something's happening at that point. We need to figure out what. Well, we're going to spend a few days on what that testing looks like, so I'm not going to talk about it right now because we got to get this one done. But like you would have to explore further and find out, is this a local max or min? What's happening at this point? The derivative, the fact that the derivative doesn't exist tells me it's not just a line that's kind of going through like that or whatever, right? Like, or that's a bad example maybe, but that's just kind of going like that. There's something happening there. We talked about it before, like what are things where the derivative doesn't exist, and one of them is a cusp. That's one of the possibilities. And there's testing you can do to see if that is what's happening there. Okay, so let's do this last one quickly. There's one more, but we don't need to get to it, but we do need to do this one. So I'm going to do some of it quickly. Bear with me. Whoops, what am I doing? I can imagine if you didn't do the practice yesterday that if I go through this quickly, you might be like, whoa, I missed that step. Don't worry too much. When you practice, you'll, I think, be fine with a question like this. So this is the derivative of the first thing, which is just 2, times the second thing, which is the square root of 5 minus x, plus the derivative of the second thing, which is 1/2, times 5 minus x, subtract 1, so that's a negative 1/2. What's the derivative of what's inside? Man, this is a mistake that's going to catch so many of us. Very good, negative 1. We often miss that. And it's a small thing, but it's enough to actually screw up a whole sketch. So try to get in the habit of watching for that. And you could, of course, have done that originally. I chose not to because I wanted to point it out. Times the first thing. Clean this up a little bit. So I've got the negative. I've got the 2's. 2 on the bottom, 2 on the top. This ends up being, I think, negative x over square root of 5 minus x. It was a negative 1/2, so it goes back to the, or it goes into the denominator, and it and it's square root. This is the part that bear with me. you have to get a common denominator. So I'm going to multiply by root 5 minus x over root 5 minus x, which gives me 2 bracket 5 minus x minus x. This is just common denominator. We did it yesterday. Over root 5 minus x. This is 2 times 5, which is 10. 2 times negative x. Negative 2x minus x is minus 3x. Over root 5 minus x. F of x is equal to 0 when the top is 0, and that's at 10 over 3. Is there anywhere that this function does not exist? Where? At 5, why?
At the bottom of the 0.
Very good. Anywhere else? Say that again?
Did you include the 0 from the original function?
What 0?
Like 2 times 1?
No. That's going to be an x-intercept or something, maybe, isn't it? But that's good. That's what we'll do eventually. But Emery?
If the square root of 5 minus x equals 10 minus 3x, would that be also...
No, that would just be 1. 10 minus 3x over 10 minus 3, something like that. No, I understand what you're thinking, but... Brad?
Is it anything more than 5?
Why?
Because it would make it negative.
So just pick a number, 10. Put 10 in for x. 5 minus 10 is negative 5. You can't take the square root of that. So we are missing a whole bunch of values here. When 5 minus x is less than 0, I will be taking the square root of a negative number. And you can't do that. So the derivative will not exist for any of those values. So 5 less than x or x greater than 5. And actually, I'm going to include all the equals to because, and I would probably actually skip that. I'm going to have to ignore that. I would have to skip that probably, and I would just do these steps and sort of do it all at once. And if you did them separately, that's fine, but you should put it together as a single statement in the end. Does that make sense? Gosh, come on.